Patrick Pollock, please come on the dais. He is an engineer, graduated in 1988 France. He started his career as a field engineer and project manager for machining transfer machine for automotive industries. Since 1995, he is a sales engineer for production machines for transfer lines automotive, heat process for nuclear applications, vacuum furnaces and processes. Thank you.
So good afternoon to everyone. I don't know, can you hear me? Yeah? Okay. So very shortly I will introduce you to my company, the company I work in. This is ECM Technology. We are a French furnace manufacturer. The headquarters is located in Grenoble in France. And we have some subsidiaries in the USA and China for the biggest one, and India. We have an office in Pune, and we are furnace maker. We have mostly the first to have invented the low pressure carburizing in mass production. And today we have 70% of the market share for low pressure carburizing furnace worldwide. And we are a family owned company making 90% of the turnover in exports. And in 2015 we have achieved 60 millions of euro with 250 people. So it's a family-owned company, and obviously the core business is the automotive industry and the low-pressure carburizing. So actually, ECM is very well known with what we call ICBP Flex. It's actually for mass production of mostly for gearboxes. This is a modular system, so actually it's a complete vacuum process. So there is in the middle like a vacuum tunnel, and on both sides they have some heating cells, up to 8 or 10 heating cells. So it's modular in the sense that you can start with 1 or 2 cells, and in the life or when the production increases, adding a lot of cells. But today I will explain you what we have recently developed in case of low pressure carburizing or carbonitriding for sintered parts. So the conventional or the well-known, let's say, processes are, first atomization, mixing of the metal powder with the binder, and then go to the press. And the green parts will be sintered in a continuous furnace, so bed furnace or Vulcan beam furnace. Afterwards, it will be finished or can be finished machines. So the issue we may have with sintered parts is the porosity, and even more than porosity, which is difficult to have then homogeneous case depths. This is a percolation network. So it means that if the pores are connected together, then obviously the carbon will diffuse faster in a certain depth as in the surface. Because also the surface will be bigger, so then we may have discrepancies in the case depths. So actually then we have to work on different parameters to avoid this phenomena. This is obviously the powder type, how to compress the parts, and what is the alloying elements to enhance the pressing and have a better density, while those elements can be also an inconvenience at the sintering phase, because element like copper has a trend to expand, while other has a trend to shrink the parts. So then we may have a modification in the sintering behavior. And chrome can be an element, but at a certain, let's say, level. Otherwise, we may have a lot of precipitation of carbides at the surface. Then we have to optimize the recipe. So the benefit of the vacuum furnace is now, I think, obvious for you. There is no oxidation at all in the surface, but as well in the matrix, and the possibility to treat grades with more chrome and less precipitation of carbides in that case. So what we have developed recently is a furnace. So first maybe a few words about the LPC process. So actually the LPC process, what we have developed since many years, it's named InfraCarb. It's a process where we have different steps of enrichment and diffusion. Enrichment, diffusion. Actually, what happened in a vacuum furnace, we can have a temperature of carburizing which is much higher than in conventional furnace because of the technology. We have some application where we can go up to 1000 degrees C for carburizing, which make the diffusion very fast, for sure, according to the Fick laws. So what happened? Also, the advantage has to be high temperature. So we are on the very high level in the iron carbon diagram, right? So we can go with more enrichment before the perlite zone, before the precipitation. So it makes everything faster, and then what we go, our process calculates what would be the maximum carbon content before precipitation, and then we diffuse to a certain level, and we enrich again and diffuse, etc., etc., and to get the final percentage of carbon which was requested. So this process can be occur for sintered part in one furnace, everything. So we have the first phase is a debinding phase at 600 degrees C. Then we go up to 1200, but can be also 1400, depends of what we have for parts. For sintering, then we have a reduction of the temperature to the LPC temperature, which can be very commonly 960. We have the low carburizing phases, and then we quench with gas. So the part is finished. It is sintered and heat treated in a one furnace. So this is some example we have. So the density we have to reach is at least 7.2 by the compaction, or let's say after the. So here we can see on the tooth tip pure matensitic structure with some retained austenite, the white spot, and obviously this is pores for sintered parts. And at the roots we have very few retained austenite, which is a carbon profile on the tooth flanks and the tooth roots. So now, just to introduce you to, let's say, new technology, but this is the revolution has been done, actually, because we have sold many of this furnace, which we call nano. It's a single flow furnace. So it's a furnace, Okay. Just a short film. I can cut if it's too long. You cannot see? So the furnace is quite different. So movie was good. So this furnace is very compact. It has three modules. One module is at the front with a gas quench, and it's also served as an airlock, vacuum airlock. Then on the both sides we have the furnaces itself. So it's the two towers with three furnaces inside the tower. So this is to treat some small batches of 500, 600 up to 250 millimeters. So it can be also installed inside the machining line. So this is, here you can see the furnace in the middle. This is, let's say, the transfer room. And at the back, we have the 10 bar gas quenching. Let's go fast because. So, which is important for this part is to have a very homogeneous speed of the gas or flow of the gas, which is performed thanks to a certain distance of the load to the high efficiency turbine, and we have a grid to have a better distribution of the gas speed. Thanks to that, we have I have sold some at least 7 to one big German company, and we may treat in a bulk some small pieces made of non-alloyed steel.
5 minutes.
Yeah, okay. Okay, then I go back to another three. So, and then also with these small parts, the advantage can be with low pressure carburizing, how to improve, okay, the hardness or the impact resistance is clear with additional carbon, and with carbon nitriding, by creating stress on the surface, we can improve drastically the fatigue resistance. And what we have the possible also function in this furnace to have a stop quench, which is basically simulating a salt bath, low temperature salt bath. Okay. So what happened? Actually, the furnace turbine is they have the control of the speed, and we can adjust, let's say, and create like like a stop quench or self-tempering phases. Thanks to that, if we compare of 29 MnCr5, so case hardening steel, in comparison for low pressure carburizing, let's say traditional or low pressure carbon nitriding, we compare and we have so direct quenching, or we have a stop quench at 130, stop quench at 160, or stop quench at 240 degrees C, which is represented in this graph. And we could compare and say that LPCN, in terms of impact, of fatigue, sorry, we can see that have a stop quench at 130 degrees C or 240, they improve the fatigue drastically. So that means that the fatigue strength is not sensitive to the stop quench temperature. Not really. No. While on the impact resistance to the stop quench, we have a better compromise at 130 degrees. So the reason of that is that 240 we have inferior bayonet on the surface to improve the impact resistance. But at 160 we have even lowest result, but it was not explained. So I'm finished.
Hello? Any questions, please? Thank you, sir. He has done MTech welding engineering, working with L&T Hydrocarbon Engineering Limited, primarily on corrosion and material selections. API certified corrosion and materials personnel, API certified risk-based inspection personnel.
Okay. Everyone, I'm working with L&T Hydrocarbon Engineering Limited. Basically, it's an engineering and EPC company. So altogether different from you guys, like who are providing heat treatment solutions or metallurgy solutions for various purposes. Today is the last talk of the last day. I understand you guys must be hurrying up to leave for your respective homes, but I'll try to be very quick because I have only 20 odd slides to share with you guys. In the last 2 days, we have listened to various speakers and experts talking about heat treatment, the recent technologies and trends on quenching technology as well. But this topic is altogether different, which I'll be taking you through. It is more of related to the application of a heat treatment where the improper heat treatment can lead to a failure of a component. First, to give you a brief background about a failure analysis approach, it requires a lot of background data and history of the component. In the absence of such history or information on the component, what has the component has faced in the past, or what were the manufacturing processes, what were the actual treatment it has faced. In the absence of those data, it is very, very difficult to predict or to specifically or very confidently say that this was the reason of the failure. But the inspection, or more of a, I can say, investigation results that you obtain out of such study can give you some insight that something was missing or something has went really wrong in the treatment of the component. So let us go through the case. The outline of the presentation would be a few basic slides, a couple of basic slides that I can skip actually. I'll go take you through the case review, what was the component and what it has seen in the past, the investigation that we carried out, the results of the same, and the hypothesis we propose could be the reason of the failure. Heat treatment, we know it is a controlled treatment of any component at a particular temperature for a particular time and a control rate of heating and cooling. It can influence various properties of the material, your strength, your hardness, and many a times your corrosion resistance as well. Talking about the case, we see Martensitic stainless steel axle over here, made up of grade SS 410. It was meant to hold an lever, or it was meant to act as a pivot to the lever arm and take the load during the firing of the missiles. The bottom image, you can see the axle failed into two different parts, completely fractured. So first of all, why 410 was selected as a material for this component? The main advantage with 410 is it offers good corrosion resistance along with good mechanical properties as well. Upon heat treatment, 410 can give you various results with respect to its strength, hardness, and maybe to an extent its ductility as well. The client specification was it required a hardness of 40 to 45 HRC, which can be easily obtained by hardening and tempering heat treatment. Now, the hardness property or more of a mechanical property can get influenced by carbon content, hardening and tempering temperature, as well as time. The approach of the investigation was in the sequence as seen in the slide. Visual examination carried by chemical analysis, metallographical examination, hardness test, simulation heat treatment that we carried out in the lab, then again metallographic and hardness test of those simulated samples, and finally the SEM analysis of the fractured surface. Visual examinations confirmed that there were no deformation or the dimension checked in the as received condition of the sample were conforming to the design specifications, but the axle was received in two fractured components. No major deformation was seen and no significant elongation was observed on the component. Whereas the third image what we see here is another axle that we have received in a bent condition, not fractured but bent condition. Next slide, you can see similar other axle at site conditions which were completely fine after test firing. No bending, no deformation, no fracture, nothing. But what has led to fracture of this axle? We'll see soon. Chemical analysis of the component confirmed that it was meeting to the specification of SS410 except the carbon content, which has exceeded the 0.15 max limit on the same. Few more points on 0.2% of carbon content, but later. The metallographic examination in as polished condition reveals a lot of inclusions and micro cracks in as polished condition. When etched with VLAS reagent, the component revealed a mixed or non-uniform microstructure of martensite, untempered martensite, tempered martensite, as well as retained austenite. So it was a very non-uniform microstructure seen across the cross section of the axle component. Now, what made us to simulate the heat treatment of the component in the lab? The non-uniform microstructure gave the hint that something was wrong with the heat treatment of the component, and we tried to simulate the heat treatment in our laboratory to just reconfirm it. So we extracted few samples from the component as seen in the image and provided it with hardening and tempering heat treatment as specified by the client. The temperature and the time constraints or specifications were of course there in the client documents. So we took two samples, hardened it, quenched it in two different media, air as well as water. The hardening temperature was retained same, tempering temperature was retained same. But we gave, quenching treatment was given in two different media. So therefore you can see two terminologies, HA and HW. HA is quenched in air, HW is quenched in water. Now this is a microstructure you can see for the specimen which were quenched in air. Now if you compare this structure with the structure in as received condition, you can clearly see that the structure now is very, very uniform of a tempered martensite altogether as compared to three different structures in same component. Again, this was consistently obtained for the water quenched sample as well, a uniform microstructure of tempered martensite. So this was again one of the points that proved that the heat treatment was improper. Now talking about the hardness result, the micro hardness test that we have gained from the sample in as received condition and in respective samples of heat treated samples in our lab. You can see very low hardness of 27 HRC in as received condition. Now of course you would ask what could be the reason of 27 HRC such a low hardness in martensitic stainless steel. Whereas we can obtain the client specified hardness of, I mean not exactly but close to it, like 39.5 and 39.8 HRC for HA and HW samples respectively, whereas the client specified 40 HRC to be minimum. The reason for low hardness could be a higher tempering temperature, improper austenizing temperature, the quenching media was something different, the quenching was not done properly. There could be many reasons, many reasons. We cannot specifically state that this was the reason of low hardness because there was no data from the vendor side, unfortunately. But we can of course propose some hypothesis like something has gone wrong in the heat treatment of the component which has led to this so low hardness, whereas this is not expected at all in such grades of martensitic stainless steel. When we perform SEM analysis of the fractured surface, we could see intergranular crack propagation along with some amount of oxide layer on the fractured surface. Now this mode of fracture or this mode of crack propagation in martensitic stainless steel can again happen or can again be the consequences of many of the improper, inadequate processing of the component. Suppose a martensitic stainless steel was cadmium or chrome plated, or maybe hydrogen charging might have happened of the component in such processing. Then those hydrogen charging in the component as well as the stress, actual stress in service of the component can lead to such type of fracture. But again, this is just a hypothesis because we don't know that the component was really chrome or cadmium plated in its history. So what were the observation from these investigations and the results that we have obtained? First of all, the component failed during the first impact itself. There were stress concentration point. If you could have observed, there were slots on the axle and that acted as a stress concentration or stress reserve points.
5
The
minutes
hard-
more. 5 minutes.
Yeah. The microstructure and hardness of the component in as received condition was non-uniform. There were inclusions and micro cracks distributed across the section. Average hardness was 27 HRC, which is less than the expected hardness. And it is important to note that this hardness was very well achieved in similar other components or axle, which performed well in the service. One of the reason of lower hardness might be the high tempering temperature. The tempering reaction or secondary hardening reactions, those are influenced by the tempering temperature. So high tempering temperature can really give you low hardness in martensitic stainless steel. Whereas simulation heat treated samples gave uniform microstructure of tempered martensite as well as uniform hardness of 3940 HRC. So to summarize the whole case, I can definitely say that improper heat treatment was provided to the sample in as received condition. The failure of the component was because of multiple reasons, maybe. First of all, there were stress concentration points, stress reserves in the component itself. The nature of the fracture was brittle. The nature of crack propagation was intergranular crack. Again, one could debate that brittle fracture, intergranular crack propagation, as well as stress concentration point could also be because of quench cracking. Yeah. But again, this could not be ascertained because the surface was free from cracks, other micro cracks that we usually see in quench crack typical cases, quench crack typical cases. So to summarize or to conclude my presentation, I would definitely say that heat treatment of any component does play an important role in successful application of the component. In the discussion part, I would like to invite opinions and perspective from you experts, because we are not heat treatment specialists, we are the end users of the component. Day in, day out, we receive such cases, failure cases in our factory, in our laboratory, wherein we come across many such cases wherein we try to figure out what went wrong actually. Because in most of the cases, vendor is very hesitant to share data from his side. Though contractually, legally it is not bounded, but they are very hesitating in sharing data from their shop floor perspective. So I would like to hear from you guys. Thank you.
Any questions, please?
As you shown that microstructure showed untempered martensite, while you are in summary conclusion, you shown that higher tempering temperature.
Yeah, the microstructure was non-uniform.
But as you told that untempered martensite was also there, but in summary you shown that there was a higher tempering temperature.
In the microstructure, if you recollect from the slide, I've shown multiple.
Just before this.
Yeah, you mean to say this
Lower
point,
hand.
right? See, the microstructure what we have obtained across the cross section was non-uniform.
And that
This
I
is
agree.
this
but,
is one of the hypotheses what we are proposing could be the reason for the lower hardness. Might be. See, it might be the case the tempering temperature might be high, but all cross section throughout the cross section area we could not get the tempered martensite.
So it may be the tempering temperature may be higher, but the tempering time should not
Yeah.
be given proper.
Yeah, exactly. So
That
in
may
some
be the main reason.
No, in some places we could obtain the proper hardness that showed a martensite and untempered martensite area, but wherein lower hardness was obtained, it was due to, again, there could be multiple reasons, written austenite as well as you correctly stated, like it could be because of time as well. Yeah,
But-
exactly. Yeah, exactly. Because in previous slide also we stated that the properties are well together dependent on time, temperature, as well as carbon content. If you have noted, carbon content was 0.2%, much higher than the required, yeah. But still, we could not obtain the hardness throughout the area.
That's why I asked this.
Yeah, exactly.
Okay.
Thank you, sir.
Thank you.
Our respected guests have delivered lectures on emerging trends on heat treatment, such as vacuum heat treatment, then on process setting parameters of CQI 9 as such, then on sintered products, and finally failure analysis cases. I hope all of us, this information is useful for all of us in our daily practices. I thank you, and I'm honored here to introduce you all of you. Thank you, sir.
We'll call upon Mr. Patrick. Yeah. Tom Sheikh. Mr. Manoranjan Patra. He has left, I think. Yeah, Mr. Sujit Ladda. Then तुम्ही द्या. तुम्ही द्या. तुम्हाला हे देतील नाही ते त्यांना तुम्ही द्या मग तुम्हाला हे देतील. And as a token of appreciation to our session session chair, Ms. Aruna, we would like to present a memento to her. Thank you. Thank you very much, all the speakers. It was quite interesting and quite enlightening for vacuum carburizing, furnace operators, and thank you very much. Just a moment. Thank you. Thank you very much. The session is over. Now the valedictory session will start at